created a class to control a stack. And we saw that creating that class was just really easy. We just used an array list or some sort of data type that was available to us in Java, and we added and manipulated that array list based on the stack commands like pop and push and those kinds of things. So the stack is that one type of data structure. So there are some other types of data structures that we need to be aware of. So let's take a look here. See if this thing will work. I did my, this is that, you know, really important Wild West theme in PowerPoint. Doesn't it look like it? Looks like a sign that got shot. Makes me feel like I'm going to Wyoming or something. So that's what we're going to look at for data structures. It's like the wild, wild west of programming. What's really cool is if you run into a data structure that you can't find an existing algorithm for, that's the fun stuff in programming, because that's when you get to really create algorithms and figure out how things work together. If I ever told you guys that story, I may have, but I'll tell you again because it's worthy. I was in Kansas City a couple of years ago at a conference, and it was for women, and they had this whole group of women that were highly successful in the development field up on stage, and they were just asking them questions, and they were answering. Well, this one woman worked for, who are the people that made the GPS? Garmin. That, okay, my brain just went blank. She worked for Garmin, and she was pretty high up at Garmin. She'd been at Garmin for a lot of years. And they were asking them what their favorite project was that they could remember. And the lady from Garmin said her favorite project that she could remember was trying to come up with the algorithms for estimating someone's movement through a downtown area, because they can't get satellite feeds to your GPS because of all the buildings and things like that. So she wrote the code that actually kind of tried to calculate your trajectory of how quickly you would be moving through the downtown area, so that they could continue to give you status updates and tell you when to turn and stuff like that. So she said for her, that was her funnest project because it was the wild, wild west, and she was getting to create those algorithms for the very first time. So that does sound pretty interesting and real math oriented. And I have some former students and brothers who both were interns at Garmin. You know, they're headquartered in Kansas City. So if you guys are interested in doing an internship in the summer at Garmin, let me know, and I'll get you a hold of Andrew and Matthew, and they can tell you all about it and how it works. And they both, I know, enjoyed it very much and learned a lot. So for us looking at data structures, we're going to be talking about how these data structures are really kind of advanced design topics. When you were in your 120 class, you started with flowcharts and you learned how to design really important data structures like decisions, right? And really important data structures like loops based on decisions. And these are the same things, just a little bit more advanced. How do we design things that use these different characteristics that we'll see in data structures? So some of the advanced techniques we're going to talk about are self-referential classes, linked lists, stacks, queues, and trees, and there are some other things that you'll run across in the textbook that are really interesting. So first thing, what is a data structure? It's just some way that we use to arrange data so that we can facilitate the reporting or updating of that data for whatever need we might need it for. So we want to make sure that we can do things properly. First of all, when we're working with groups of data, we're always working with collections, right? So if we have an array, it's a collection. If we have an array list, it's a collection. If we have a list, it's a collection. So all of those different data types are collections of things. So what about collections? Are they all sets? Like you could have a set of Easter eggs or a set of baskets, or what a set of precious moments. A set implies that there's no duplicates. So if you see that word in the textbook, a set of data that's in this array, they're assuming there's no duplicated elements in that array. Now a list is assumed to be ordered. So again, we can have some things, some assumptions behind the scenes. Another assumption that we have is a queue is first in, first out. We'll look at it. All right, here's a linked list. We're starting right here at the hard part. That was a, I don't know why it's not moving. Oh, well, he's supposed to look at something and say, I hate linked lists. A linked list is a data structure that's pretty advanced, and it's a sequence. And I want you to think about these here at the beginning so that you have them in mind. When I'm looking at a linked list, I'm looking at pieces of data that are connected by reference links. So this first piece of data that's at the front of my list has a little pointer built into it, and that data is a memory location that points to the second piece of data in my linked list. Then that piece of data has a memory location associated with it that points to the next piece of data. When I get to the end of my linked list, that memory location, that address of the next item in the list is set to null, or some sort of value that indicates this is the end of the list. So when we're looking at a linked list like this, we call the beginning of the list the front, the end of the list the rear, and we have all of these connections in between all these reference points that create our linked list. So why would this be better than an array? When I have an array, remember all of my entries must be contiguous in memory. They must be side by side by side. Would I have to have that way with this? No, because each entry is going to point someplace else in memory to the next entry. So they could be scattered all over the place, but they point to each other. So now instead of having to have 32 gig to hold this array, I'm going to have my storage requirements spread all out in little pieces so that I don't have to worry about that giant piece of storage. So a linked list internally, one item is going to point to the next. If we're using a Java class to access that, we don't even care. We don't even care that that's going on behind the scenes. To us, we can use it just like an Arraylist or any of the other collection items that we might use.
Another advantage is you don't have to sort it to stick something in the center.
Exactly. He's got another advantage. Here's a few more. Our array has to be fixed size, declared at creation. With a linked list, we can just keep growing, just keep adding more entries. Whenever our array is built again, it's fixed. The linked list can grow. We can add new items independently of any of the other items. Now, one problem with a linked list is when we add or remove items, it's time consuming because we have to update more than one entry, right? So if I add an entry in the middle, I have to update the previous entry to point to this new one. I have to point to this, make this new one point to the next one. So it can be a little complicated and definitely time consuming, but it's possible, whereas with an array, it wouldn't be possible without rebuilding the array. Now, whenever we're looking at a linked list, the list node class gives us information about each of the nodes, the data and the pointer that points to the next node in our linked list. The list class itself keeps track of all of those different nodes. So if we're using a list class in C#, we're using a linked list behind the scenes. So the list class is keeping track of the first and last node. It's got constructors to initialize our beginning references to null. It has methods to allow us to insert at the front and the back of the list, and remove from the front and the back of the list. So we can do lots of things with that. We could have an exception. If we're working with a list, we could have an empty list exception, and that would just tell us that we were trying to perform an illegal operation on an empty list. So these linked lists are behind the scenes, and Java's using them to keep track of some information. There are some different types behind the scenes, or we could create our own. A singly linked list is one like I showed you in the first example, where each node has a next pointer that points to the next node. This one becomes circular because our last entry points back to our first instead of having a null address. So it's circular because I could just keep looping through those entries without ever ending. Now I could also have prior pointers, and that would mean that each node not only pointed to the next entry, it also had a pointer to the prior entry. And if I have a doubly linked list like that with next and prior pointers, not only can I walk forward through my list, I could walk backwards too. So I could get the previous entry. Now, if I'm looking at a doubly linked list like that, it's going to cause even more overhead to update it, right? So I'm going to have even more pointers that I have to update properly to insert something or remove something. Now, just like the list that only had next pointers, this doubly linked list could also be made circular, where my last entry's next pointer points to the first node, and the previous pointer of my first node points to the last one. So I can make them all go in a loop all the way around. These linked lists, before we move on, these linked lists are actually the basis for the early databases. So whenever you're in the SQL class, if you think about a database and all of the entries that are in a table, they really are entries that are linked list nodes. And that's how the database management system is able to handle everything in a really good way. Okay, so what's a stack? We talked about them last time. They're LIFO, last in, first out. Seems dumb, hate a stack. I don't want to be stuck in a stack. If I'm the last one in, I should be the last one out. Well, with our stack, don't forget, we looked at the stack of plates. The last one that was put on top of the stack is going to be the first one taken off. So that's why it's last in, first out. This is a constrained version of a linked list. That means Java is going to say, all right, I got a linked list back behind the scenes, but to you, it's going to look like a stack. And I'm going to give you methods like push and pop so that you can make that stack work. Now a queue is when we're waiting in line. So I don't have any good pictures. I need a good picture. This PowerPoint is not the picture one. Let's find a picture. You guys have probably seen a picture of standing in line. You probably know what it looks like, but it's always good to have a visual. So all of these are queues, right? And if you say quay, you would be wrong. It's a queue, and it's also not a QU. It's just a queue, and that's because it's a European word, and so that's how we say it. It's queue. I don't know how many ways I've heard it said. Have you guys seen that one picture that keeps going around social media that shows the 30-lane highway in China coming down into 3 lanes? That's a queue. That's a queue for you. I don't think there's any rules to that queue, though. I don't think the first in is the first out in that one. But a queue is normally FIFO, right? First in, first out. If I've been standing in line for 4 hours, it's finally my turn. I get to have my turn. That airport one always gets me. I think it was last year, these guys that were in my class last year would laugh at me, but I got up to the line in Springfield at the airport, and I had to wait in line. I can't remember why, some sort of problem where I couldn't just do the check-in. And so I was waiting in line, and I waited and waited, and I can't remember what was wrong. I was using a cane or something where standing in line was really hard for me. And it was finally my turn, and I was up to the thing, and somebody comes up beside me and just went in front of me. They had paid for that like VIP check-in or something, which meant they totally got to cut in line.
I bet you weren't used to cane.
Oh yeah, I wanted to VIP them, that's for sure. So we get some differences in queue processing with things. So that queue is not supposed to work that way. Whenever we get those new rules that just violate all of reality, that's our problem, right? But so here's our queue. We stand in line nicely. We wait for our turn. If we were the first one in line, we should be the first one out of line. Queues are really cool, and it's a really big thing. You know, there are whole like majors. There's a master's degree majors whose topic is queuing theory, because queues are actually a really cool thing to study. You know, you can watch a queue, a line, and see how long does it take? What's the average length of time a queue takes to process, right? Walmart does a lot of that. Can you imagine? They have a lot of people that do queuing theory. And then they decide, well, it doesn't really matter. We're just going to do self-checkout anyways. And so we don't really care how long it takes. Because, so we can get away from it there. But there are a lot of studies of it. My daughter's done a lot of traveling. She says that, not to be like stereotypical, but she says that Asians don't acknowledge queues. Is that true? You've seen a lot of different people in the world. She says like they were at, where's the Pope live?
Oh, Vatican City.
Vatican. Ah, I'm just having, sorry, those bad words today. It's one of those things I should probably go home. But she was at the Vatican waiting in line, and you have to wait in line like 6 hours or something to get in there. And so people brought like supplies for the whole day and be in line because you're inside, I guess, sort of this like tunnel area where you're being queued through until it's your turn. Sounds like torture to me. But that's what they do. And so everybody just waits in line for as many hours as it takes because they're going to get in there to see the Vatican because you only go there once. And she said that the Asian people, mostly the Japanese people, will cut. And she said they would stand there like as a whole family because if you notice, they usually travel with a lot of family members, but they would be kind of large group and they would slowly like send somebody up. And then other people would slowly follow that person up. And before you do it, this whole family would have cut and be like an hour ahead in the line. Huh?
That wouldn't be Japanese. That might be Korean or Chinese.
Maybe Korean or Chinese. Asian of some sort.
Yeah,
she said she didn't want a stereotype.
Japanese are totally polite.
They are overly polite, but you know, as things have changed time-wise, they've become a little more aggressive too with lines because I think because of the overpopulation in Japan. The island's shrinking, so there's like more issues. Yes, sir.
That a lot in China.
In China, sneaking ahead.
Yeah, just like kind of
I think it has to do with the huge population.
yeah. Beijing is like everywhere.
Everywhere people were doing it.
Yeah.
Well, it really annoyed Heather.
Not subtle at all.
So that violates queuing theory. We are not supposed to have people clumping and jumping when they're in the queue. They're supposed to stand in line and acknowledge the queue. So look at these rules. We have rules. You can only add to the back of the line. No cutters. You can only exit from the front of the line. So it doesn't matter how many hours you've been standing there tough. You just got to tough it out until it's finally your turn. We're FIFO, first in, first out. If you get in the queue, you are NQ'd. If you get out of the queue, you are DQ'd. You're out of line now. When we are thinking about a computer system, the processor has a queue, right? All of the commands that are waiting to be processed by the processor are going to sit there in the processor queue. Print spooler, that's a really good example of a computer's queue. If I send a bunch of jobs to print, they're all going to sit there in order waiting till their turn. Network transmissions actually use a line queue type theory where if we all send a network packet at the same time, they're going to kind of get in line, and the first one in will be the first one out pretty much. It's clicking on the wrong thing. Okay, let's try this here. Okay, so what's a tree? A tree is a data structure that has a nonlinear structure. So with a tree, we have a root node. Here's our root node. And then we have two or more links off of the root. Whenever we're working with a tree, we're always going to try to kind of keep it even. So we're going to have a left subtree or child and a right subtree or child. When we get down to the bottom, we're going to have the leaf. So it's a lot like we would describe a file system structure is a tree. We would have the C drive and all the folders and then all of the files as the leaf structures. So the tree structure is actually used that way to denote a file system layout. So we do use it. Now in this tree structure, each node has been assigned a numeric value. If you look at the structure, you'll notice that they're kind of split evenly. If I added the number 81 to this tree, which side would it go on? the left or the right subtree. Because we keep everything balanced and that number is too big because on this side, the highest number we have so far is 43. So we would look at, if we want to add that new number, we would look at our root, and then we would look at the left subtree and the right subtree to decide which tree we should be adding that new node to. We would see that the right subtree is greater than the left. They're both less than the number we're adding. So we would know that we would add that new node to the right subtree.
And to the right of 68.
And to the right of 68. So whenever we walk a tree, we have three possible ways to do it. We could do it in order, we could do a pre-order, or a post-order. It says to review this figure. That was me being lazy. Let's see if I can find it. I wish I had page numbers. Let's see. We'll ignore that. Picture there and just think about it here. So if I want to read our tree structure in order, I'm going to start at the top, and I would just start at the top, and I'm going to look for my left branch, and I see my left branch, and then I'm going to look for my left branch, and I would keep looking for that leftmost branch until I reach the bottom of my tree structure, and that's going to be the least element, the lowest, okay? So I would output it, then its parent, then the item to the right of it. Then I would move up, output the left item, the parent, and the right item. And my tree is going to be built as such that that structure is going to continue on all the way from the top to the bottom. So that would be me walking it in order. Pre-order would be we process the root node, then we process the left subtree, then we process the right. And post-order would be where we traverse the left, then the right, and then finally the root. And these are pretty advanced data structures. We would use this tree method if we were doing some internal creation of our own, where we wanted to create some operating system type capabilities or keep track of something in a really efficient manner. Because normally we're going to let those Java classes that use those structures behind the scenes take care of things for us. Now, if we have a binary tree, everything's going to be tightly packed. I'm going to show you a video in just a second about that. But let's look at this one first. If I can get everything to work. We'll just let that commercial play while I...
Let's look at boxing. It used to be a really big deal back when .NET first came out because we didn't have generics. But now that we have generics, boxing isn't so much as a big deal, but it's still there, and we should be aware of boxing when it happens.
We'll see if this is worth it.
Hinder performance of your application.
He's showing a C#, but it's the same.
If it does hinder performance, you use profiler to show you where that performance hit is. You'll understand what's going on. Just as I did in previous videos, let's draw the smaller. We draw the memory. This is just kind of an arbitrary way of drawing RAM. We know that RAM is divided into stack and a heap, And here in main, I'm going to say int I gets 5. Then I'm going to say object O gets I. Well, when I first say int I gets 5, that makes room on the stack here for I, stuffs the value 5 and that 32 bits. When I say object O gets assigned what is in I. So here is O, and O is a reference. O is a reference. And since it's a reference, it has to reference things out in the heap lab. It can't reference the stack. So it looks like, if it's going to reference, it's going to reference to something down here, but that's not legal in any way, shape, or form in C#. You must reference something in the heap. So how does this work? Because this certainly works in the builds. I could say console write line O here, control F5, and it builds and succeeds, and we get the output 5. So what exactly is going on here? Well, this is boxing, essentially. It has nothing to do with the sport. The runtime, the CLR says, oh, okay, you want to assign O to this value type that's stuck on the stack, and O must reference something out on the heap. So what the runtime does, without really telling you, is it makes what it's called a box, which is a fancy way of saying it grabs some RAM, it puts some info up in here. We won't be concerned about right yet, but there's some info, and then it also puts the value of the 5 right there. All right, so I is a separate entity from O is referencing something out here on the heap. I can prove that. Let's console write line I and O, but before we do that, I am going to say I gets 20. All right, so if O was referencing I, then both of these would print 20 to the screen, but I'm telling you that O is referencing this boxed object out here. We'll see 5 for O, and we will see a 20 for I. So let's control F5, run that, prove that that is the behavior we see, and there you go. Now say I want to change the object that O is referencing. Say I want to change this value up. All right, well, as far as the box is concerned, there's no way with this integer, the way it's boxed, that I can modify this value. So if I do want to change O, let's say O gets 99, and then console write line O. Can you imagine what's going to happen in that case? To pause the video and think through what's going to happen when I say O gets 99. How is my diagram here on the right going to change? Go ahead, pause the video, think about it. Okay, let me control F5 this. You see, yes, certainly O on this last print is a 99, but we didn't modify this value here, this 5. Okay, what happened is that the runtime again saw 99. Oh, that's an integer, it's a value type. You're assigning it to a reference, right? And how do we reference something? Well, we need to box it. So it creates a new box. I have some meta information up here. Don't worry too much about it. And inside that box, the boxed integer. So here's the 99. Then we assign that to O. So O is no longer going to point to this box. It will point to the new box. And now you can see the old box is open for garbage collection. Right? That's one downside about boxing is if you do a lot of these boxes and you're not paying attention and assigning value types to references, then you create a lot of boxes, and that puts pressure on the garbage collector, one, because the garbage collector has to maintain a consistent heap. It also could defrag the heap. That's also part of garbage collecting, is to compress the heap once in a while, defrag it. If you really defrag your hard drive, the same idea happens with RAM. You fragment it as we allocate, and free this thing up. But then I want to allocate some more, so we'll allocate something bigger here, something bigger there, and a small thing here. And then all of a sudden I want to allocate something this big, but there's no, this thing won't fit here. But it might, if I move this here and compress this here, I'll change those things, I'll probably be able to make room for it. That's the same idea with the garbage collector. It has to compress that so we can, even though there is enough room to allocate this thing, we just need to crunch everything together. Everybody, if you sit on a bench at a venue or a movie and they say, everybody scoot into the middle, make room for people on the end. That's what they're doing there. They're compressing their room. In case what we're doing here is the same idea. Anyway, so there you go. What I want to do for the next video, I'm going to give you a little puzzle and then let you.
We'll stop him there because I'm not going to let you guys watch him. He's out there, Jamie King, but he's doing C# stuff. But he did a pretty good job explaining that boxing thing that goes on in C# and Java. So it doesn't matter whether we're talking about C# or whether we're talking about Java. We saw it last time when we were talking about generics. Generics can only be used for an object data type. We can't use a generic with a native data type. Now we're seeing that when we're working with data structures, again, we can get impacted by this boxing and unboxing of our numbers that we said were an int data variable, and we try to move them into an array list or some sort of data type that said that it's going to take integers, the object type. So we have to be aware of that happening. Let's look at one more thing here. Let me find it. When we start looking at data structures, we need to think about the things that we do with data structures. So if I have an array of items, one thing that I might need to do is search through those items to find something. Can I find it? I want to find this other animation just a sec. See if I can find it without finding the place where I have it. Silly girl. Okay, finally. So if I have an array and I want to search through my array and I want to find something in the array, we know that there are methods we could use for the array class. There's methods we could use for the array list class to search for something. So we may not have to write the code ourselves. We might want to write the code ourselves depending on efficiency. But even if we don't write the code, we know what's happening behind the scenes. This is what's happening, a linear search. So right here I have this array and I want to find this key 8. So what I'm going to do is begin looking in the array. The first step I take is going to look at array entry 0. It's going to check the data in that entry. It says, oh, there's a 6. That's not equal 8. That's not the one you want. So we're just going to step to the next array entry. You're looking for 8. This one's 10. Oh, it's not the one you want. So we're going to step to the next entry. Still not the one you want. Keep going. Still not the one you want. Keep going. Still not the one you want. So to be thinking about how many data accesses are occurring here as we step through our array. Finally, we found the entry that has that key. So we can start over. We did our search. It's complete. So that's a linear search. That means we're just going to go straight down the line and look at each entry in our array to see if it matches. A more efficient way of doing it would be a binary search. I didn't change that right. Let me fix it. So with a binary search, if I can get this in here, I always try to get everybody to think about the Price is Right. And when you are watching the Price is Right, because everybody's seen the Price is Right, right? There's that one game, higher, lower, where they have the prize and you're supposed to guess, is it higher or lower? Well, think about the people that play that. Have you ever watched those people that are dumb? You just want to reach through the TV and slap them, right? It's like, stop it, stop it. You can't go 1, 3, 5. You're never going to get the right number, right? If this prize is between 1 and 1,000, what should you guess first? 500. Then if he says higher, what should you guess next? 750. Then if he says higher, what should you guess next? Something 750. 875. He did that really fast math. So we're doing a binary search. We're cutting it in half, and then we're going towards that half. that we just cut it. And that's exactly what we want to do when we're programming, if we want to search for something and we want to find it faster. Now, if we want to do that, if we want to do a binary search, notice our data has to be in order, because we can't split it in half if it's not in order. It would be meaningless. So for this binary search now, we're looking for the number 8. We have the same array, but it's in sequence now. So when we do our first step, we're going to say, oh, 10 is the middle of the array. Position 9, actually, index pointer-wise. Does it match the key we're looking for? No, it doesn't. Is our key higher or lower? Lower. So we're going to eliminate the whole top half of that array. We don't need to search it anymore. And then we're going to look at the middle of that bottom half. We've got a 5 there. Is the entry we're looking for higher or lower? Higher. So we're going to eliminate that whole bottom half. And now we're down to just those few entries to search through to find that item. So if you notice, it took us like 4 times or so to step through this one with our binary search, and it took 7 or 8 tries with the linear. If our number 8 had been at the very end of our array in that linear search, it would have taken us 20 times, right? Potentially, we could have had to search through that whole array to find that entry. With our binary search, we would never have to search through the whole array. We could have a situation where we might have to search 3 or 4 entries, but we're never going to be looking through the whole array. Okay, so we have lots of different data structures that we can use, and let's take a look here at some really simple examples. And I want to go to chapter 20. So if you can find Ravel, let's go to chapter 20 that talks about stacks or list stacks, queues, and priority queues. Now, some of these chapters start getting a little bit overlapping, and sometimes they might talk about some things that you've never heard about before. And they do that because I think they've rearranged this book a lot over the years, and sometimes when they move chapters around, they didn't update the prereqs, you know, and they still refer to things that aren't there anymore. So if we're looking at this thing, I hate that black background. It's making you guys go to sleep. So you can always use the links in your textbook in this online thing to jump around. If there's a topic you don't remember ever hearing about, you might be right. You might not have ever heard about it, and they might be acting like you did. And it might be because we did the chapters out of order, or it might just be that you forgot about it. But you can use these links to jump around in the textbook to get to all the different places that you need to go. Now, when we begin chapter 20, since we're talking about collections, we want to review some of these key collection points. And let's look at the collection in the Java hierarchy world. Here we are with a stack class. So it's way out here. It inherits from many different classes. The stack actually inherits from the vector class, which inherits from the abstract list, which inherits from the abstract collection, which, what really matters, inherits from collection. So all of these different data types inherit from the original collection class. So that means whatever capabilities we have in the collection class, we inherit all of those capabilities in all of these other collection types. So if we look at the collection class and the collection interface, what kinds of things does it give us? Well, they have like a method is empty, a way to convert this item to an array, a way to add an item to the entry, a way to clear it. So we have some pretty common methods for all of our different collections that we can use. So let's create this test collection application listing 20 .1, and then we might be able to use it as we go for some of our other applications here. So I want to open NetBeans. So I want to create a new project, and I'm going to name this listing 20_1. And then I'm going to make my main class be test collection. Now in this one, they use a collection name that's really long. So let's try and shorten that down a little bit. See if I can zoom in here. Now, when we are working with these data structures, we're going to lose some of those skills, those JavaFX skills that you guys developed. So anytime you want to create something as a GUI, feel free. So if you turn in an assignment and it's got a GUI interface, but it didn't call for it, that is never a problem. So, always happy to see that if you want to turn something in that way. Now, for this application, since we are going to be more console-based again, we're going to be putting a lot of stuff in our main. So we're going to start out with declaring an array list. Now, the array list was introduced to you a while back, but when we did it, we hadn't really talked about generics. So the array list, if you remember, always use that greater than, less than diamond, and you just always put the data type that you wanted in there. So that, now we know what that is. We're going to call this COLL1. Oh, that looks awful. Let's not do that. I don't think so. CO1, that's better. Just can't have all those L's and all those ones. So we'll do CO1 and then we'll have a second collection too. Collection is just a little too long for us. Now this is going to be a new array list. And for our constructor, remember we don't need to specify the generic data type, and we don't have any parameters to pass to that constructor. Now if you want to Alt-Enter to add in that import, that should be fine. So we'll be looking at java.util.ArrayList. Now let's add CO1. I want to add, we'll add some cities. New York, Atlanta, Dallas, and Madison. Seems like a poor fit, doesn't it? Poor little Madison, Wisconsin, with all these big giant cities. Now let's print them out. First, we'll do a heading line, a list of cities in CO1. And then we can actually just name our collection in our print line statement. Now let's do a little bit more. Let's output a question. We'll do a new line first. Is Dallas in CO1? Now we want to add a true or false. So we're going to use CO1 dot contains, we'll use the contains method, and ask if it contains the string Dallas. Now let's run that. So here I've got my list of cities in CO1. Notice if we just do the print line with the collection name, it prints the collection all on one line with the square brackets and commas in between. So that's why we usually do some sort of loop to print them out ourselves, but we can print it that way. And then it did find Dallas in our collection. It says that it returned true. So notice some things about that contains method. Did you get back any information about that data that it contains? No. Did you get back the index location of where Dallas is in that array list? No. All you got back was a true or a false, which might be exactly what you need, but it might not. Now let's continue on and let's remove Dallas. So CO1 dot remove, and we want to remove that Dallas entry. Now after we remove Dallas, we're going to print out a little bit more information. Let's do a new line and then some more things like CO1 dot size. And we'll add a little bit more. After that, we'll say cities are in CO1 now. So let's run that again, and we should see our collection. And then we see that at the end, there are 3 cities in our collection, and of course we started out with 4. So cool, pretty easy for us to work with. Let's create a new collection. Now this is going to be a little bit different. So notice the syntax. Because Arraylist inherits from the system collection, we can actually say that we want to create a collection with a generic data type of string. We'll call that CO2, and we can say it's a new array list. Now, I'm going to get the error there because I need to import javautil.collection, which I will. Didn't do it for me. I did something. Didn't click on something the way it likes. So when I'm working with Java, I can actually specify a parent. Here is the data type. And then I can specify a more specific data type in the new implementation. So I can say I have this thing that's going to be a collection. It's a collection type of information. But then when I instantiate it, I specify, oh yeah, it's actually an array list type of collection. So notice how our data type at the beginning of the statement and after the new keyword can actually be different when we're talking about classes that inherit from each other. Extending classes. So Arraylist 2, or our CO2 collection, let's put some stuff in there. Is it giving you a hard time?
Yeah,
What's the matter?
CO1 dot remove. It doesn't like CO1. Oh, I know why.
Found it, okay. Sorry about that, we want to add, let's add Seattle. And Portland. And LA. And Atlanta. Again, Atlanta just does not belong to that list, but that's all right. Like we should start singing that song, which of these things doesn't belong here. Then I want to print out another heading, a list of cities in CO2. And we'll print out our CO2 collection. Let's run it. Bless you. And here's our second array list. Everything looks good. Nice and easy to work with. Now, a couple of other things that we can do with our array lists. Let's clone one. We'll create an array list of strings. And let's call this clone one. Now, I can't just say new, though, because I don't really want to make a new array list. What I want to do is clone an existing array list. So I want to tell it which array list I want to clone. CO1. We want to do a clone command. Now it's very, very upset at us. It says incompatible types. I can't convert this CO1 to an array list. So we're going to have to cast it. So I'm going to cast it, but my cast is going to look a little different. I'm going to say, oh, I'm casting you as an array list, but I can't just say array list. I have to say array list with a string data type. Now, once we've cloned that thing, let's print it out. Clone one. I want to try that before we add this next thing. So the last thing we got Seattle, Portland, LA, and Atlanta, and then our New York, Atlanta, and Madison. So that looks right. That's our cloned list. Now I'd like to take that clone list and I'm going to do what's called a retain all. And we want to add our collection 2 into that clone list. Oops. Too many lists. So our clone 1 list, we want to basically add in all of our collection 2 cities. And then let's print that out again. And now clone 1 should have all of the cities from our first list and all of the cities from our second list.
Interesting. That's not what I was expecting the final one to be.
So what did we retain there? All of them?
Just the ones that were different. No,
Just the one that was different?
no, that was
The one that was the same.
Just the one that was the same. So we only retained an entry that we found in all of them. So that's kind of an interesting way to name that too, that we want to retain only the one that has. Now let's start with that again. Try one more. We're going to do a new array list. Do this differently. We're going to say clone 1 equals, we want to go back to that collection 1.clone again. We can just do a little bit different syntax here. Since we've already created it or declared it. I don't want to declare it again. So we're going to recreate it. Now it's going to start over with whatever was in our CO1 collection. Now that we've got it in our CO1 collection again, let's try clone 1.remove all of the things that you find in collection 2. And then let's print it. So our retain all gives us only Atlanta. Our remove all gives us everything but Atlanta from our CO2 list. So you can kind of try some of those different methods. There's a lot of capabilities and some of them might not be exactly what you would think that they would be. Is it all working? Here's some clicking still. Let's comment some things out. We're going to use this same program. I want to start out with our beginning collection. And then after we create our New York, Atlanta, Dallas, Madison collection, let's comment out the rest of our code. I'm just going to do it manually. Leave my opening or closing curly braces. Now for this one, after we've got our collection created, we're going to use an iterator. An iterator is a class that is kind of associated with a collection class. So any collection class has an iterator, and that just means how do you walk through this collection? How do you decide what all is in this collection? So an iterator is one of those system level classes. We're going to create an iterator that processes strings. We'll call it iterator. And it is going to be our CO1.iterator. Now I'm going to need to add an import. Now when we're working with an iterator, it's controlling, like I said, the walking through our collection. Because think about this collection. If this is just a standard array, then we just want to start at the beginning and walk through it. But if this array list is being used as a stack, we don't want to walk through it maybe from the beginning to the end, depending on how it's been set up. We want to go from the end to the beginning. If it's a queue, we want to process it like a queue. If it's a tree structure that it's holding, then we'd need to process it using that tree structure. So we can't just step through using a for loop, because some things are iterated through in a different manner than other things. So we'll see more about this. We're just getting started. Now for this one, we're going to use a while loop, and we're going to say while this iterator has things to process, it has a next, I want to do some things. And what I want to do is print out the iterator next. And then I'm going to go ahead and set it to uppercase. And add a space. And then after we've printed that, I'll go ahead and print out done. If we run that now, we see our output. Notice it's a little different than when you just printed out that whole collection, because when we just printed out that whole collection, the runtime system printed it out with those square brackets around it with commas in between each entry. This let us control how it was printed out. So each entry has its own line. I could change it to a print statement instead of a print line and get back to that output that looks a lot like the system. So that's fine too. Bless you.
Thank you.
So anything that has an iterator associated with it can use the for each statement. And we love the for each. So now let's comment out this iterator stuff. I think I'm going to do a little bit more commenting here and say iterator processing C20.2. Wrong place. Go down here. I'm going to have my separate commented blocks. Now, whenever we have an iterator, we can use the for each, and it's not much different. It's just that it gets us away from having to declare this iterator object. We don't have to instantiate it. We can just use the for each. So we can say, oh, for CO1, I want to use a for each. That was weird. Be nice to me. Let's see, it keeps giving me for each final. So for each thing in our list, we can do some things. Now, the for each command uses this lambda expression. This for each, there are lots of versions of it with Java. But when we use the for each that actually says for each, we're going to be doing a lambda expression that says what lines of code should occur in the for each body. And we're going to specify those with the E:, our event. So what we want to have happen in this one is just an output, and we want to print each E into uppercase format. Plus we want a space character. So I'm going to make that a print again instead of a print line. So So we'll look here in a second at the alternatives to that lambda expression. But basically now, this for each should give us kind of the same exact thing as this iterator with the while loop. So let's try it. You should see your output there. New York, Atlanta, everything perfect, just the way we wanted it. Is it working?
Yours is turning it across.
Take out the line. Yours printed down?
Yeah.
Print line. Take out the line.
I just made it print.
You made print.
Now in the Revel, there's a couple of show and tell type things here. So first of all, this is the for each the way we used it. This for each uses the lambda expression. So the lambda expression, it says it's equivalent to using an anonymous inner class. It simplifies the syntax. Okay, so if we use this lambda expression, E becomes the name of each of our items in the collection, and we process each of the items in the collection within that lambda expression body. Now, another example, way that we could have that coded is we could say that we have a new java.util.function consumer in our collections for each, and then inside that we could have the default for each method, which is accept. So yeah, I think the lambda expression is much simpler than that anonymous inner class. And then this is the syntax that we will see probably most commonly. In this syntax, we use the for instead of the collections.forEach. And in our for loop, we specify that for each item in this collection, at the end, this is the collection name, we want to call each item E, and we want to do the body of our for loop for each item. So this is kind of the simplest one, or maybe more similar to other programming languages, maybe. But either way, they'll all work. You can use all of those different syntaxes for your for each loop. Now, as we go through, as you look through your text, they're going to tell you a lot about some of these classes that are available. Our Arraylist and our linked list class are going to give us a lot of capabilities. Let you go through that one on your own. This is where we want to go to the comparator. So this is listing 20.5. Let's create it. So I'm done with this one. I'm going to save everything, and I'm going to create a new project. This new project will be listing 20_5. Our main class name will be geometric object comparator. Guess what that means? Gotta find all that geometric object stuff. You can find it. Mine's working on it. I think it broke. Finally. Okay, so in this, I need to find my geometric object and my rectangle and my circle. Let me see where I can find those.
I've got mine on the desktop.
You've got yours just right there. You're so good.
I just need to know where that is.
Just copy them into your default package. Now, we have them last in listing 19_3. So if you have that one, you should be able to copy them. Hang on, and I will post them to the chat.
works there. It's worked pretty well. Really? Okay, click on the right hand project. Click on that one. Yeah, there it is.
Does everybody have it? Do I need to post it? Will it let you post it to the chat from your desktop, since you have them in such convenient places?
Let me see if I can.
Mine are buried down in these projects. I might be able to copy mine to the desktop too. That's a good idea. I'm always leaving everything where it's supposed to be, and then I can't find it.
I would probably have to open them and do them individually. It's not letting me cut the whole file. Was that me that did that, or was that you that just did that?
You did it.
Okay, gotcha. Yeah. They're there.
Okay, Jim's got them out there in the chat. If you need them, just save them and then copy them into our project.
Yeah.
Rectangle and circle.
And geometric object. So when you look at your project, after you've copied those, you should, under your default package, you should have 4 .java files. Our new one, our geometric object comparator, the geometric object and the circle and the rectangle. So you might have to save it, download it
I
from
was
the
about to
chat,
say,
and then paste it in
I
there.
originally saved them to the desktop, and that's why they.
The desktop is a good place since we seem to be using them a lot. No? For mine, I just said copy this time. I was tired of that. Okay, that just seems it's gonna change that package name if it needs to. Yeah. For our default.
But if you cancel, you lose them.
Yeah, you lose them. Do they not even stay in the old place?
No, they just disappear from the new.
Oh, they just don't go in there.
Put it in source, or do we put it in?
Put it under source packages, under default package. And if you have a package name, you would want it under there. And if you have a package name, then you do need to do that refactoring, and it would fix that package name for you. But you could fix it yourself too. Got him, got him, got him.
She's getting her last one now.
Yay. All set? All right, let's create this thing. We're going to start out creating our geometric object comparator. And our geometric object comparator or comparator or whatever is going to specify how you compare one geometric object to another. Now, we've done this already before, so it should look really familiar to you. It's just that when we did it before, we did it for the routine that was going to sort these kinds of objects, right? Which one is bigger? Now we're going to be implementing a method for the comparing of the objects so that we can search through the array to find things and any other thing that we need along those lines. Now we need to add an import for the java.util.comparator. Comparator. And it does have an uppercase C. So I do not need a main in this class. I'm going to get rid of that. And our geometric object comparator implements the comparator, the system level, using a geometric object. So we have a lot going on in our class statement here. So whenever we use the implements keyword, are we inheriting that class or implementing an interface? Implementing, because we were using the implements keyword, so we must be implementing an interface. So the comparator is an interface, in this java.io.serializable is an interface, and we're using both of them. Now, in order to use the comparator, we must create a method, compare. Now, our compare method is going to take as input two geometric objects, two things to compare. So we're going to have object 1 and object 2. And those are the two things that we're going to want to compare. We're going to start out with, hang on, get big, there it is. Sorry, I was like, I can't see it. We're going to start out with a variable to hold the area of our first object, and we'll use the O1 get area method to find that. So in that case, we just called the geometric object get area method for our circle or rectangle. Now for our area 2, we're going to load that with the area of our second object. Now finally, we're going to compare them. If area 1 is less than area 2, we're going to return the -1, meaning the first is smaller. Else, if they're equal, we're going to return the 0, saying that they're equal. Otherwise, we're going to return a +1, saying the first item was larger. Now, whenever we were working with sorting, our method name was compare2, and we weren't implementing the comparator, we were implementing the interface that allows us to sort. So now we're implementing the interface that allows us to compare things to each other, to search through things. We have to implement the method compare. So once we've created this, forevermore in our world, we don't have to create it again. We now know how to compare two geometric objects. We could use this for sorting. We could use it for searching. We could use it for checking to see if one is greater than another, whatever we wanted to do. So think about this from our business's point of view. If our business deals with customers, maybe what we want to compare are the customer's annual sales, right? Is customer 1 better than customer 2? In our mind, they're better if their sales are higher. So we could implement our compare method that compares them based on the amount of sales. Now, if there was something else we want to compare them on, maybe we want to find all the customers that are closest to us distance-wise. We could create a compare method that checks to see how far away they are from us, and the ones that are closer would be our favorites, would sort higher. So we could implement that compare method based on our data and our needs. What things do we need to compare? All we have to do is create this compare method, and now we've built ourselves right into that Java runtime system that now knows how to compare our type of objects with each other.
Quick question.
Mhm.
The Java IO serializable, was that
Mhm.
something we need?
We need it, but they don't really say much. This class also implements serializable. It is generally a good idea for comparators to implement serializable so they could be serialized.
Okay.
So they don't really say much about it. I know that serializing means that we could like encrypt the data in our class. So apparently if we don't have this and we say that it implements the comparator, then we cripple our ability to encrypt.
Why is it not like nice geometric
Probably that imports. Because we got the comparator in in the wrong place.
I drove it was so tiny, I couldn't see it. I'm like, what's happening? But not have it right.
She used that as
I'm like, okay, so
Actually, I want to see
That's
how.
weird.
No, it still doesn't work.
Still doesn't like it. You mean it's a lowercase?
Oh.
I thought I saw that shifting going on. Okay, so now we've built our comparator. Let's update our main so that we can use it. Now the main is, where is it in our geometric object class? I think so. Let me find it.
I don't think there is a main.
There isn't a main. We'll have to make one. We'll put it in the bottom of our comparator. Actually, I think I'm going to make a new one. Let's right-click on default package, and we're going to create a new Java file for our tester. So let's do new Java class, and let's name it test comparator. And we'll put our main in there ourselves. Oop, I got a typo. Let me fix that. I right-clicked over here and said refactor, rename. Now I've got my main in. I'm going to put in my open and closing curly braces. And in our main, let's create an instance of a geometric object, G1. And we'll say this one is a rectangle. So again, we're using that syntax in Java where we're specifying the parent as the data type in our declaration, and then we're mentioning the actual class that we want to instantiate after our new keyword. I hate it that way. But it's very, very productive because you can do things however you like. And then we'll create G2 as a circle. That's 5. And then we'll create another geometric object. Let's call it G. And we're going to create it using our max method. If you remember from way back, the max method returns the larger of 2 geometric objects. Now don't worry about that max giving you an error because we're going to create it. Because if you remember, our old max method only took 2 geometric objects. We're changing it up a little bit to use this comparator. So we'll be adding that in just a second. Now, after we've done that comparison, let's output the area of the larger object is g.getArea. Now we want to implement that max method. Our max method is going to return a geometric object. And as input, it expects a geometric object that it will call G1, another geometric object that it will call G2, and a comparator that uses a geometric object. And we'll call that comparator C. Now, because we passed in, this one needs that import. Because we're going to pass in our comparator to this max method, we can use it. So we can say if, using our comparator, using the compare method, comparing G1 to G2, if the output is greater than 0, meaning we got the 1, we would return G1. Our first one is greater. Else we would use G2. Yeah, there's a bug in there, isn't there? How do you want to fix that bug?
Show an equal sign after the comparison first.
Which one are you going to send back? If they're equal, it doesn't matter which one we send back,
Exactly.
right? Okay, so what do we want to do? Else if,
I was just gonna make it greater or less than or equal 0.
okay.
Because if it's 0,
Like that?
yeah, or greater than or equal, doesn't matter for what we're doing.
Because we want to use
Yeah.
G1.
So in that one equal sign,
Mhm.
it should,
Because if they're equal, it doesn't matter which one we
it
return.
doesn't matter which one.
But the else clause would not have worked in every case with that. Sometimes they're thinking of really high and lofty stuff when they're writing this book and they're not thinking about the bugs they created. Okay, run it. Does it work?
No main bus is found. Okay, let's try this way. There we go. Get return to value.
That's the right one. It should be 78 point whatever.
539.
Mm-hmm. That should be our larger one. So whenever we're looking at implementing the comparator, just like the previous example, we could replace that with a lambda expression if we wanted to. So our compare method is the default method for, excuse me, the comparator. So we could use the lambda expression if we wanted to get the same results. Let's do this last one and then we'll quit for the day. I want to create one more new project. It'll take us half a second. This one is going to be listing 20_7. And our main class is going to be sort strings by length.
Yeah, I went down with three.
Oh, sorry.
That's okay, I'll just leave it alone.
We'll fix you.
Problem is the math is wrong on the classes thing. Yeah, you're having a problem with the math? Or with the math? The math is wrong.
The math isn't wrong. The if statement is.
So either one of those would equal. Well, I guess it would. Never mind.
Okay, good. Because I was like, I don't know. You're doing geometry. I'd have to ask the computer.
Did you do a new file or new one? I was bringing the circle.
We did a new one.
New project?
New project. And we made it listing 20_7. And we made our main name sort strings by length, but it doesn't really matter. In this one, we're going to see a nice simple example of the comparator. Because our previous example was great. We're getting used to that geometric object. But let's do a nice simple one too, because that's kind of always helpful. So in this example, in our main, let's create a list. So we're going to create an array of strings called cities. And let's just put some cities in here. Atlanta. We're going to be in Georgia for a minute. Savannah. Leave in Georgia. New York. And Dallas. Have you seen all those storage tanks burning in Houston? Does not look okay. And I say it's okay to breathe. When I worked at Conoco, one weekend we left town, and when we got home, the smell was really bad. One of our friends was an engineer responsible for burning off waste. And he said that weekend they burned off some waste that they saved for like 5 years. They only burn it off once every 5 years because it's so awful. 5 women miscarried that weekend that I knew of that worked at Conoco. So some of those smells can be really, really not good for you. Now, whenever we look at this here, we're going to do the full length sort. We've got it fully qualified, the name there, that it's in the Java util arrays library, and we want to use the sort. And what we're going to sort is our cities array. And in our cities array, we want to use a comparator. We didn't tell our engineer friends about how many people in my department had miscarried because it would have been too much for them to handle because they would have felt responsible, and they weren't. They just had to do the planning. Okay, let's do a for loop then. Now, we're going to use the for loop syntax that was the last syntax they showed, where we say for data type, variable name, colon saying in what collection. Our collection is cities. And what we want to do is print out S, which should be our city name, plus a space. Oh, and I want to print, not print ln. Now, in my main, the only error I have is on that comparator because I haven't created it. So I've got a little bit of a problem there. So let's create it. It's going to go right under our main. And we're going to say that it implements the Java util.comparator, and it uses the string class. We'll actually use our @ override statement for this one, which we could have for the last one. But we're going to say our compare method uses two strings, S1 and S2. And we're going to return the length of those strings. Actually, which one's longer? I'm going to have you tell me how this is working. So whenever we're doing a compare function like this in Java, we've learned that if the first one is greater, we want to return a positive value. If the first one is lesser, we want to return a negative value. So is this math going to work for that? It will, right? Because if S1 is longer, we'll be returning a positive value. If S1 is shorter, we'll be returning a negative value. So what we'll be returning is basically the length of the city name. So once we get done with this sort, our cities should not be in order by the letters in their name. They should be in order by the length of their name, right? Because that's what we set this comparator to do. So let's run it. Sure enough, I see Dallas as the shortest name. Should we put in some longer ones? They're all kind of the same length. I like some short ones. What's a short one? Can't even, huh? Ava. That's a good one. I want to make sure that thing shows up first. That's a very good one. Ah, there we go. It was.
I hate doing this too.
That's all right. We're done. Let's done it with trial.
Oh, add an N and an H to it.
Oh, I don't
Apparently,
remember
the way
that.
you've got it, it is the shortest.
Oh. It just.
No, that one should have been an N and an H. Doesn't matter, just add another one. Put a character in there, doesn't matter.
Okay, no wonder.
So that just
And there you go.
Okay.
Because it was by the length.
Oh,
It was the same length as Dallas, we originally had it, so it left it at the front order because it's the first one came to.
So this means, again, by comparing, I could have a method that does some sort of player logic that says, oh, whoever has the high score is going to sort to the top, or whoever has the low score is going to sort to the top. Because remember, I could be looking at a whole object here that has all sorts of different data elements, and I could be comparing these objects based on any of those data elements. Maybe I want to sort it by how long ago it was that they last logged on, so I can see who hasn't logged on in 6 months. Maybe I want to sort it by who has an overdrawn checking account, so I can list those at the top. Who has the most money? Who makes the most money? Can you think of other ways that you would want to sort things? It's just endless, depending on what you're doing, what your thing is in fact that you're doing. Is everybody's working okay? Yeah. Keep that one. In another class that I was in, we were working with the Android developer tool, and of course it was using Java. They kind of have a little bit of a different language now. We might try it like Kotlin. I think we can see if it's on these computers, but it should be very Java-like. But we were trying to figure something out, how to make a list on the little list view on the phone display. And one of the students came in all excited, and he told everybody else, and he's like, I just put in a compare to. I just put in a compare to. And was able to make everything sort the way we wanted it to sort. It was so easy. And it was like, awesome. You know, that everybody was able to figure it out. So keep these things in the back of your head as ways to solve problems, because they're kind of cryptic and they're kind of hard to remember that you have this capability out there. We are about out of time. Any questions?
It's not about this. It's not about the GitHub.
Oh, okay. Let me stop this.